or something like that. Well, scientifically, they do the same thing in malware. We have a way to determine if something's malicious or benign based on either machine learning, data science, or whatnot. So a lot of these, analysis that, right, and on top of that system, next one, kind of like supervising what is it in order to do something. Think that it allows you. I was always taught that, but from which is pretty much the badass assembler of reverse engineering. And you might also need some Red Bull because you're going to be looking at a lot of machine code as much as possible. You'll be sitting there for hours trying to stay awake. Figure out what you're doing. You'll have to know like what offsets and what functions you need to go to first before you actually start debugging. And so this is your pretty much your car. All right. And then finally, a process monitor is basically just showing you what type of processes are running on the box while you're debugging. Because you never want to miss something like, say, it spins up a new process and you didn't catch it. Well, this will tell you it. And then a network monitor. I just wanted you to see what this looks like. I actually use INetSim for my network monitoring. Basically, what it does is it acts like a fake internet, and then it'll sniff all of the traffic that's coming from malware or your guest operating system. All right, operating systems. The only concept of what I want you to know here is that there's two modes. There's user mode and kernel mode, typically in x86 operating systems. All right, the one that I want you to focus on is user mode because kernel mode, it's like a hot mess. And I'll show you why. Next slide. So pretend these are processes, right? And the squiggly marks, that's like all the memory within the process. Kind of like what we saw before with all the pink and blue for the memory structure for PE, right? So we have all these processes. Process memory, right? Everyone has their own. No one touches the other. That's all and this is kernel. Everything's shared. So you'll have to work with other kernel drivers to make sure that you're not sharing the same memory. So you have this thing called altitude, which you may not want to know yet. But it kind of helps you determine which memory is yours. And then next one. You can tell this one is a work in progress process. All right, back to this layout. So the only thing I want you to know here is that the memory grows towards 0. So when you're analyzing a process and you're looking at the stack, it will subtract until the amount reaches 0. Well, the heap is the opposite. It will grow until the beginning of the program. So when you're working with memory, you got to know, where you are as you're analyzing it, right? So if you have these basic concepts, you'll know where you're at. All right, so here's the stack. Next. Cats. Just like all right, so this is an example of a push. So what is exactly doing? Because the stack grows downward, right? We're subtracting for the size, say it's 32-bit, then it's only 4 bytes, right? So -4. So each time you add a new address or value onto the stack, subtracting 4 from there. And it's kind of what I was trying to explain earlier, is that when you're trying to follow things on the stack, remember it's going backwards, right? And then push. So the next one is the heap. Cats. All right, thanks. So whenever you say heap alloc, or you're creating a new buffer, basically what you're doing is you're saying, here's a pointer to the heap. What flag to say is like what permission it is or whatever. And then you say you want just 2 bytes. Usually that's not the case, but for cats, it is going to be 2 bytes. Next one. So it allocates the space within the heap. And then once it's done allocating the space, whether it's 0 or whatever, it will turn the pointer to the new place where it allocated. Yep, there we go. And so when you, after you're done doing heap alloc, what you'll get is the pointer to the address of the heap where you just allocate that memory. All right, little Indian. So when you're looking at the stack, all of the addresses are backwards. So you're going to have to remember, like when you're looking at it, I'm at the point where I see it, I'm like, okay, A, B, whatever. And you're going to have to recognize it that way. So you might get lost in trying to remember where you are because you forget that it's a little Indian. Everything is backwards for address spaces, for addresses on the stack. All right, now we're going to go down a rabbit hole. Hopefully I'm good on time. I'm trying to pack as much as I can within 45 minutes. So with assembly instructions, these are basically, when you parse the hex data, you get assembly. And there are three main types that you should remember. There's data movement, which is just moving from one address to another. Arithmetic or logic, say you're doing and or if it's add, subtract. And then control flow is basically changing the position of the CPU as you're executing every instruction. Next. So here's an example of a C program versus how it would look in assembly. So let's correlate these two. Next. All right, so this is actually a branch instruction. It's basically an if statement. So if the flag does not equal 0, then go jump to else. And it's kind of like the else that you see up there. It's kind of a weird way of doing a if statement. Next. And then we have an arithmetic instruction, which is just add 1 to EAX, which is just a container for I, in this case. And then data movement. So we want to make I equal 0. So because we know I is EAX, which is just a container, right? It's going to move the value of 0 into EAX. It's all backwards, unless it's in. All right, so the main thing that I want you to get is that you can take control of the program if you wanted to. So as you're looking and you're debugging, you're able to control whether it takes if statement or not. How do you do that? By these wonderful flags. Each flag means something. The 0 flag, say if 1 equals 0, if 1 does not equal 0, so then it would be the 0 flag, right? If it did equal 0, it would be set to 1. So, in this case, next. Say we're comparing EAX to 0. So, because 0 equals 0, the 0 flag is set to 1. But when we get to the next one, say we want to take this jump, right? We can change the flag if we wanted to as we're debugging and force it to take the jump or not take the jump, depending on how you flip that flag bit. All right. Hopefully you're still with me. Assembly instructions. So one of the things that I want you to learn is like how it looks like in assembly. So here's basically printing a string, Shecurity, right? So let's see how it looks in memory or in assembly. So when you make a function call, it pushes the argument onto the stack, and then it pushes the return value onto the stack. Right, so this is where it pushes the argument security onto the stack. Next. And then before it makes the call, it pushes the return value, which is the next instruction, onto the stack. And then from there, once it makes the call, this is the stack space of the actual function. So it moves up, growing to lower. Okay. All right, each new function call has its own stack space. If you kind of think of it when you're moving from a new place, right? You have to make sure that you have a house to live in before you move to that new destination. So you have to allocate a new house, right, in order to go there first. It's kind of like a function executing on the stack. You have to have memory there prior before executing all of your variables. So when a function runs, like, a new function in a new address space kind of grows downward. And then it'll keep growing. And when a function is done executing, it will remove that information from the stack. So when you're debugging it, this is what you'll see abstractly on the stack. All right, now we're getting into malware techniques. I kind of give you a basic overview of assembly and kind of like the core concepts that you need. You don't necessarily need to memorize the assembly instructions. You can just Google them as you go find them. I wasn't like an assembly expert either. I was probably like close to failing my assembly class, but after time went on, I started to learn it. It's kind of like if you're fluent in a language, then you're going to get used to it. All right. So I'm not sure how many times you've seen the execution flow of malware. Usually it's called the cyber kill chain, but I didn't want to use that word because it's a buzzword. So we've got stage 1, stage 2, stage 3. Reconnaissance is basically what a lot of pen testers do. They'll start probing the network to see where they can get in. Yeah. And then, yeah, okay. And then exploitation. A lot of people are familiar with this as another way of infiltration. You don't have to go through an email to get onto someone's box. You can just use a waterhole attack and try to exploit something and get onto their box. But the easiest way is to do email phishing, because some user's going to click on something that's interesting. All right, and then internal reconnaissance. This is where once they're inside, they're going to start looking around and scoping out your network so it can know where to go next. And then from there, entrenchment means, say you want to reboot the box, right? But you need your malware to restart after the reboot. So you set a couple of keys or set up a stage where how the malware can survive the reboot. So whatever way to make sure that it's always persistent on the box, right? And then you have command and control. This is basically talking to a server. Like they've done a pretty name on it, but this and then exfiltration is basically taking a bunch of information from the user, the box, whatever they want, and sending it out to that server. And then finally, purge. Usually I don't see purge with a lot of crappy malware, but advanced malware, they'll go out of their way to remove themselves or make it harder for forensic analysts to find it. All right, infiltration. So I tried to find the crappiest stock photo I could. But this is not what I mean by the infiltration. All right. So typically infiltration is, what they'll do is they'll go to LinkedIn, they'll find out who works at your company, and then they'll try to spin up a fake email posing as that person. So most of the time I've seen CEOs, CFOs, HR departments, they will try to get other employees to click on a link or open the box from the email. So here's an example. This one's from Bleeping Computer. It was pretty interesting. It has a PDF attachment on there that forces the user to do something because they think, oh, it's from HR, they got to do something about it. And so I'll show you an example of how to look at a simple Word document. I just want you to be aware of how to recognize something that looks malicious. So this was actually, my husband got this email for me. He always gives me all his malware. And it was in French. It was French. Because he's French. So what I want you to do is not ever, when you open a document from an email, and you're doing this in a VM, mind you, don't ever turn on enable content thing. So what that means is I'm allowing you to execute scripts within Microsoft Word. So next slide. So what I want you to do is go to the macros, view macros, and look at all this junk data, right? And you go edit, and you can see that this is a script that's actually being executed. What this is actually spyware, but they obfuscate it so much that you pretty much don't know what's going on. But as a reverse engineer, you have to painstakingly try to deobfuscate that. And there's a bunch of tools to do that, or you can just do it in Word right here on a VM and try to figure out what they're actually trying to do. All right, internal reconnaissance. So how would you tell that you're connected to the internet? Ping, right? Would you try to contact Google or Microsoft Update, right? So that's typically what malware does, is once it gets on the box, it says, am I connected to the internet? What are the closest adjacent boxes to me? So you'll start to see that in the second after infiltration, that they're just going to start looking around and trying to do network stuff. All right, entrenchment. So this is where I say the most interesting part, and an easy way to identify malware is through their entrenchment phase, because they try to put all of their goodies in spots that you can't find. So what do I mean by that? So in this case, this one was doing software Microsoft Windows current version run. So what is that spot? So in registry, if you were to reboot the box, it would automatically run whatever you set that key to. So most of the malware, it's very common for them to do this, is set themselves to that key so that next time it reboots, it will start up and do its thing. And so you can say reg create key, and then reg set value, one more. Yeah. So I just wanted you to see what this looks like in assembly, even though I'm trying to show it to you next as how it looks like in the original code. So I actually wrote this. This is the actual source code. Basically what it's doing is doing all of the ritual lyrics and putting it in registry keys. I wrote you tests that are fun. So you can see here's the original C code, and then the assembly code, which kind of looks similar, but you kind of get an idea that this is not as bad as you think it is. I mean, assembly is just another language for you to learn, and how you know how after compilation, what does it look like? Because every compiler is different, every language is different, and they'll come out differently. You have to get used to recognizing the differences in coding styles. Oh yeah, and there's reg create key, and then there's set value. All right, assembly functions. Remember how I said arguments are pushed onto the stack, right? But they're pushed on the stack backwards. Everything's backwards in assembly. So you can see here are all of the arguments for reg create key X, where it pushes 8765431 onto the stack. So when you're looking at it and you're debugging it, you'll see them all be pushed onto the stack backwards, which is nice because you need to know what those arguments are. Because you're going to have to be the one to figure out which key it sends so you can go get rid of the key. Right. So I kind of put this map, and I show this map all the time. I put this together on how my opinion on simple to sophisticated, as well as common to rare. So you have auto runs, which you can see it's kind of like in the middle. That was the key that you saw earlier being sent. So the most challenging to detect is the DLL loading, DLL hijacking that you see in a lot of blog posts, as well as boot execution, which is very rare. But I'm not going to get to those. I just wanted to show you just kind of a layout of different types of persistence mechanisms. All right, command and control. So there's three different types of. So there are different types of things, but the basic thing that it wants to do is get through the firewall to talk to its server. So I wanted to show you an example of what that looks like in assembly. Next slide. So this is still the rickrolling malware. You can actually go to that website, latimes.com/world, welcome to cyberwar.1-1, and it'll show you the YouTube video. But what this is it's setting up an internet connection, Internet Open A. If you're coding in C in a different language, or on like Linux, it might be different. But on Windows, they're using these specific API calls. And you can see how it looks from the original code versus assembly. That's all I want to show you, just how it looks. All right, so there are three common types of C2 data that you're going to see. The reason why I'm showing you this is because when you see the communication out, it's usually encrypted, or you don't understand it very well, so you need to reverse engineer it in order to understand what kind of information they're sending out. So the typical HTTP request, and this is from my RE 101 course, definitely not malware.com, obviously, you know, it's delicious. and what you'll have to build is a lot of these strings that are in the malware are going to be obfuscated or encrypted. So it's your job to rebuild this whole GET request somehow. So this is non-HTTP traffic. So what that means is it's not in that cute little GET request, right? It's just a bunch of bytes. So if you think of the malware plugx, the typical, I guess, actions that it does is that it will download a new module and then plug it into the malware. So in this case, this subcommand is basically telling the C2 node what to do. So these 8 bytes, the first and the second, are something that only the server can parse. But it's your job to figure out from the malware, like what the hell is it sending back to the server and what is it going to get back, so that you can recreate the traffic, right? Because you're going to have to create a smart log or some type of firewall rule to shut it down. And then, covert channel. So this one is very rare. Usually what they'll try to do is find find a hole in your firewall by sending bytes through a channel that's allowed through the firewall. So in this case, a DNS request is pretty simple, right? But did you know that you can do a query on the request? From in that query, you can actually put in junk byte data into the request and use it as a way to ship bytes back and forth from your server. Next. All right, I used a really bad, overused stock photo again. But like, next one? Why?
Exfiltration.
So, exfiltration, basically what that means is just extracting data out from the user or the computer that it's on. And so there's common targets. One I just explained, user information and credentials on there. And then system information. Usually when they're doing internal reconnaissance, they're going to send system information out to the C2 node to tell it what type of operating system am I running, what version of Windows am I running, so that I can send my new executable to execute properly and not crash, so that, everything works properly. And then high-value files, documents, and pictures. Usually, if it's an APT or corporate espionage, they're going to try to steal documents and send it back. If they're smart, they would just email it or encrypt it and send it back to the server if they wanted to. All right, I wanted to do this crazy concept. Last night, I was actually trying to reverse engineer Chrome just to get an idea of how this technique is used. So let's take Chrome. Let's make him happy. All right, and so let's extract out Chrome.dll. So Chrome.dll does all of the hard work for Chrome, but as well as using SSL methods to send data back to the servers. So if you wanted to look at non-encrypted data, you would define that SSL method. So what I've seen malware authors do is find the offset of the SSL writes and hook it. So what does hooking do? So hooking will, the hook will take, stop there. It's okay, it'll automatically go.
Oh, okay.
Yeah. So what the hook will do is it will replace the pointer to SSL write to your own SSL write. And then so all of the arguments, including the buffer of data that you're about to encrypt, is going to be sent to that function. So when you have your fake function, you could do evil stuff with the buffer, like find a password and scrape that buffer for passwords. And so this is usually called spyware. What it'll do is it'll try to steal credentials from browsers by hooking the methods within a browser or application. If you're familiar with game dev, cheating usually is the same way. It'll find a method inside of the game, try to hook that, and change the output of the actual function. All right, the takeaways. Next. Two. All right, so I showed you some tools. I just wanted to get you familiar with some of the tools that I use on a daily basis. Get you just to see what it looks like. I don't want you to be intimidated by all of this night code, even though you might need a Red Bull at the end of the day to get home. All right, yeah. All right, and I wanted to show you what memory looks like and get an idea of the memory concepts and operating system names and everything. I want you to be able to correlate low-level assembly code and higher-level programming languages so that you know what you're looking at, and you can recreate that to make unit tests, or maybe you want to write your own malware for pen testing. You can do that too. But mainly, it's a blue teamer thing. You need to figure out what it does in order to stop it. All right. And there's different parts of the execution flow which you will start your process of analysis in. Say you're looking at the second stage or the third stage, but you never saw the first stage. So there's different ways and you can recreate this whole execution flow so you know how to deal with it when you're trying to protect your network. And then we looked at some malware. If you really want my Rick-rolling malware, I can use it. All right, any questions?
So I just took a class in forensics as give them, primary everything.
if you're in a junior role, you're usually assigned a mentor. That helped. I learned when I'm 2. What would be like? Tools. I try to implement myself, and I don't trust any of my tools because sometimes you trust that things are the same or.
Like website also. Work in San Francisco, dude. No one uses Windows.
Oh yeah, you can. IDA's on Linux too. Like it's on Linux OS X, everything. Yeah, you can use Hopper. Hopper does PE executables too. I haven't used Hopper myself, but you might try Binary Ninja, Radari, or IDA 3. IDA 3 just came out with 7.1. Should be Linux available too. Sweet, thanks. Any other questions? All right, thanks.
Hello, everyone. Just a couple of quick announcements. We have a few minutes, but at 12:15 we will be having a town hall here. So please come ask all your questions and start a dialogue. Jaya is going to be leading that, so it's a great opportunity to ask someone with 20 years of experience questions. Upstairs, 5th floor.